Um, what if the biggest mistakes you make in life actually happen before you even realize you're making a choice?
Oh, that's such a great question to start with.
Right. I mean, we usually think of math as just, crunching numbers, just staring at a test, calculating a fraction, and hoping you don't get a giant red 42 circled at the top of the page.
Yeah, the dreaded red ink.
Exactly. But today's source material suggests we actually have that completely backward. Welcome to today's deep dive, everyone.
Yes, welcome. And for this deep dive, we are looking at a textbook. It's called Opening Up High School Mathematics A, Counting, Probability, Geometry, and Number Theory Made Clear.
And look, if you're out there thinking, I don't really need a high school math review right now, stick with us.
Yeah, please do, because this book isn't actually about memorizing formulas at all.
Not at all.
It treats math as like a framework for organizing choices, managing uncertainty, and structuring logical arguments in what is an incredibly chaotic world.
And to really anchor how this works in practice, the book shares this story of a student named Mia. So Mia gets a 42 on a math quiz.
Ouch.
Yeah. She's sitting in this quiet classroom after school, looking at her paper, and she just feels totally defeated.
Yeah.
I think we've all been there.
Oh, absolutely.
The formulas in her head are just a tangled mess. She views every math problem as a trap, just waiting for her to step into it. But her teacher, Mr. Mizuno, he steps in and helps her make this tiny shift in perspective.
A crucial shift, really.
Yeah. He tells her a math problem isn't a trap, it's a blueprint. And that red 42, it isn't a verdict on her intelligence. It's literally just a map of her thinking.
Which, I mean, that completely neutralizes the panic right there. When you see a problem as a trap, your brain freezes. You're just operating out of pure fear.
Right, fight or flight.
Exactly. But when you see it as a blueprint, you realize, oh, I just have to look at the structure. I can trace the lines. And the very first structural pillar they tackle, and really the first one we need to look at today, is how we counter possibilities.
The illusion of formulas versus the reality of counting. I love this part. The book makes this really bold claim that the biggest mistakes in counting problems happen before any arithmetic is even done.
Because human beings just rush. We see a word like choose or arrange in a problem or, in a real life scenario, and we immediately try to grab a formula from our memory banks.
Just to get an answer as fast as possible.
Right. But the foundational rule of counting, according to the text anyway, is to organize before you calculate.
Wait, so the secret to counting isn't adding, it's organizing.
Exactly. You have to understand the nature of what you're counting before you even assign a number to it.
Okay, let's unpack this.
Well, the most crucial dividing line in counting is understanding the difference between a permutation and a combination. And it hinges entirely on just one question.
Does order matter?
Yes. Does order matter?
Let me use a corporate analogy here to test this. Imagine you have a team of 5 people, and you need to pick 2 of them. Scenario A is picking a CEO and a vice president. Scenario B is just putting together a 2-person task force to look into a new software program.
That captures it perfectly. So in scenario A, picking person 1 as CEO and person 2 as VP is an entirely different reality from picking person 2 as CEO and person 1 as VP.
Right, the roles change.
The roles change, the power dynamic shifts. If you switch the order, the outcome changes entirely. So that is a permutation. Order matters.
But in scenario B, if I pick person 1 and person 2 for the task force, it's the exact same task force as picking person 2 and person 1. There are no titles.
Exactly.
The group itself is the only thing that matters.
Yep.
Order is irrelevant. So that's a combination.
Yes. And what's fascinating here is the reason people struggle with the mathematical formulas for these concepts, they just memorize that a combination involves a fraction.
Like they just memorized the rule.
Right. They don't understand that the division in that fraction is literally just a tool for erasing duplicate realities.
Hold on. What do you mean erasing duplicates?
Well, think about your task force. If you use the permutation method to pick 2 people out of 5, the math gives you 20 outcomes. But that method is blind to the concept of a team.
Oh, I see.
It counts person 1 and person 2 as one outcome, and person 2 and person 1 as a separate, distinct outcome. It counts every single pair twice. So to find the true number of unique task forces, you have to divide your total by 2.
Because you have to mathematically slice out all the echoes. You're stripping away the redundant arrangements.
Precisely. If you are picking a 3-person task force, a group of 3 can be arranged in 6 different ways, so you divide by 6. You are mathematically erasing the arrangements of the exact same group so you don't overcount your reality.
Wow. See, that points to something much deeper than just high school math for me.
How so?
Well, why do our brains naturally default to treating combinations like permutations? It feels like an ego thing, you know? We assume hierarchy and order always matter.
Oh, that's a really interesting point.
We think we have 100 unique, distinct problems in our lives, but maybe we just have a few core problems showing up in different arrangements.
It's a fundamental cognitive bias. We overcomplicate our lives because we fail to recognize what actually makes a scenario unique. We think changing the order changes the substance, and I mean, most of the time it doesn't.
Right.
And if you're miscounting your options because of that bias, your assessment of reality is already skewed before you even make a decision.
Which means assessing the actual risk of those options is going to be a disaster. And I think that explains why Mia hit a wall when she moved from counting our options to calculating probability.
Yeah, she was reviewing this classic two-dice problem with Mr. Mizuno. Find the probability that the sum of the two dice is a 7.
Right. Standard math problem.
Right. And Mia looked at her dice and saw 11 possible totals. Everything from snake eyes, which is a sum of 2, up to double sixes, which is a 12. Since there are 11 possible sums, she used 11 as her denominator.
Okay, I'm looking at this from Mia's perspective right now. There are exactly 11 possible sums on those dice. 7 is one of those sums. Why isn't it just a 1 in 11 chance? Intuition tells me she's completely right.
It absolutely makes intuitive sense until you confront the core requirement of probability, which is, are all of these outcomes equally likely?
Oh, wow.
Yeah. To roll a sum of 2, there's only one physical way that can happen in the real world. The first die must be a 1, and the second die must be a 1. But to roll a sum of 7...
You could have a 1 and a 6.
Yes.
Yeah.
A 2 and a 5, a 3 and a 4. The sum of 7 happens in 6 different ways. The sum of 2 happens in only one way.
So they aren't equal at all. Treating them like they are equal is a complete distortion of the physical reality of the dice.
Exactly. The true denominator isn't the 11 visible sums, it's the 36 hidden ordered pairs, the 36 physical combinations of how the dice can actually land.
Those outcomes are the equally likely ones.
Right. And this leads to one of Mr. Mizuno's most striking points in the entire textbook. He tells Mia, the denominator is the world you are considering.
The denominator is the world you are considering. That is so profound. It's almost like trying to figure out your odds of winning the lottery, but you're accidentally calculating the odds for a completely different game.
Yes.
You're not bad at math. You're just standing in the wrong universe.
And if you choose the wrong world as your denominator, your fraction is meaningless. The math might look perfect on the page, the division is correct, the numbers are neat, but it's describing a reality that does not exist.
Which people do constantly in business and in life.
All the time. They calculate their chances of success based on a distorted denominator of possibilities. They think their odds are 1 in 11, when really they're 6 in 36.
But, here's where it gets really interesting. Even if you define your world correctly, calculating your way through it can still be a complete nightmare. Which brings up this massive shortcut the book introduces, complementary events.
Oh, this is one of the most powerful shifts in thinking the book offers. So let's say you're rolling a die 4 times, and you want to know the probability of rolling a 6 at least once.
Okay, if you try to calculate that straight on, it's a mess.
A total mess.
You have to figure out the odds of getting exactly 1 6, then exactly 2, then 3, then all 4. And then you have to, stitch all those messy separate probabilities together into one master equation.
It's an exhausting amount of calculation, and mathematically speaking, more calculation means more room for human error, but the complement flips the script entirely.
How so?
Instead of calculating all the exhausting ways you can succeed, you just ask, what is the absolute opposite of getting at least 1 6?
Well, the opposite is getting 0 6s, getting none at all.
Right. And calculating the odds of 0 is incredibly easy. You just find the probability of not getting a 6 on a single roll and multiply it across the 4 rolls.
And then what?
Once you have the probability of utter failure, you subtract that number from 1, which represents 100% certainty. What remains is your probability of the event happening at least once.
It's like walking through the back door of a problem because the front door has 5 different deadbolts.
Exactly.
If figuring out how likely you are to succeed is too complex, just figure out your likelihood of total failure and subtract it from your reality. Whatever is left over is your success.
It's such a profound way to assess risk. Don't chase the 50 variables of success if there's only one variable for failure.
But, okay, calculating the odds of a reality is really only half the battle.
Yeah.
Once you figure out what's true, you actually have to convince someone else that it's true. And that is where Mia hit her next wall-writing mathematical proofs in geometry.
Yeah, geometry is typically where students realize they can't just trust their eyes anymore. Two lines might look perfectly parallel on a page. An angle might look exactly like 90 degrees, but appearance isn't proof.
And that creates this immense blank page paralysis.
Hmm.
You hear the word proof, and you think you have to write some intimidating formal essay.
Yes.
You sit there staring at the paper, and you don't even know what the first sentence should be.
Right, the essay trap. They think a proof requires elegant prose. They think it's about sounding smart. But Mr. Mizuno steps in and completely dismantles this. He goes up to his chalkboard and tells me that a proof is not an essay. It's just a blueprint.
Just a blueprint.
It's exactly three things. An assumption leading to a reason, leading to a conclusion.
Okay, let's put this in adult terms, because I feel like this happens in corporate meetings every single day. Imagine someone tells you a flight is delayed because of weather.
Okay, yeah.
That's not a proof. That's an assumption. If a proof is a blueprint, the reason is the physical bridge connecting the raw data to the final claim.
Exactly. So what does the bridge look like for the flight delay?
Well, you can't just say weather equals delay. You have to build the bridge step by step so everyone else can walk across it.
Right.
So step one, the radar shows a severe thunderstorm over Chicago. That's a given fact.
Right.
Step two, commercial planes are mathematically not permitted to fly through severe thunderstorms due to turbulence limits. That's a structural reason.
Makes sense.
Step three, our plane's assigned route goes directly through Chicago airspace. Another structural reason. Therefore, conclusion, our flight is delayed. You have to show the beams connecting.
And geometry is essentially the training ground for building those beams.
Yeah.
If we connect this to the bigger picture, it trains us not to accept claims at face value.
Right, you can't just assume.
Exactly. Someone tells you two angles are equal. Why? Are they alternate interior angles? Are they base angles of an isosceles triangle? You have to provide the structural beam. As Mr. Mizuno tells Mia, seeing is the beginning. Proof is how you let someone else see it too.
Proof is how you let someone else see it too. That really gets to the core of why so much communication breaks down today. We live in a society where people just, scream their conclusions at each other without ever providing the bridge of reasoning.
We expect people to just trust our eyes. We say it's obvious, but obvious isn't a proof. If you skip a step in your logic, the whole structure falls down. Geometry forces you to trace your logic all the way back to the foundation every single time. It strips away the emotion and leaves only the architecture of the argument.
So we've got our blueprints. But getting those raw materials to build the blueprint is another skill entirely. Solving any complex problem requires translating messy, real-world conditions into organized structures.
Right.
And more importantly, it requires knowing what to do when those structures fail.
The translation piece is where a lot of people freeze up. The textbook gives a great example of this. You get a word problem that says, an integer leaves a remainder of 2 when divided by 5. Right. If you just stare at a sentence like that, it feels incredibly dense. Your working memory immediately gets overloaded trying to hold on to the concept.
It's total word soup.
Yeah.
You read it 3 times and your eyes just glaze over because you're trying to do the math and remember the rules at the exact same time.
But if you translate that sentence into a structural formula, if you literally write down n equals 5k plus 2, suddenly the fog lifts. The words become a visible, workable piece of machinery.
You aren't straining to hold the concept in your head anymore.
No, it's right there on the paper, ready to be manipulated.
You're taking the invisible and making it visible. But let's get to the hardest part. So what does this all mean when things go wrong? What happens when you do all that? You organize your counts, you define your denominator, you build your proof, and you still get the wrong answer.
Yeah, that's the real test.
What happens when you still get that 42 circled in red ink?
This raises an important question, and this is where the book's philosophy is so vital. It goes way beyond high school. Think about what we do when we make an error. We look at the right answer, we nod, we write careless mistake next to it, and we just move on.
Careless mistake. It's like the ultimate rug to sweep our problems under.
It really is.
But why do we do that? It feels like we use the word careless to protect our egos. If I say I was careless, it implies I'm actually smart and I know the material, I just wasn't paying attention. It's a defense mechanism to avoid feeling incompetent.
That is exactly what it is. It shields us from having to admit a flaw in our fundamental logic. But the book insists you cannot do that. You have to give the mistake a specific clinical name.
Like what?
Was it an omission? Did you confuse a permutation and a combination? Did you choose the wrong probability denominator?
You have to diagnose the exact mechanism that broke down.
Yes. Because if you just label it careless, it remains emotional and vague. You learn nothing. But when you label it mathematically, when you say, oh, I treated a combination like a permutation, You neutralize the emotion.
It's no longer a personal failure.
Right, it's just a mechanical glitch. And a mechanical glitch has a specific countermeasure. You know exactly what to look out for next time.
So let's go back to Mia, sitting in that quiet classroom as the sun goes down. She's looking at her quiz. In the beginning, that 42 was a record of her failure. It was absolute proof that she was bad at math and bad at thinking.
Yeah, it was a trap.
But after walking through these concepts with Mr. Mizuno, after actually naming her mistakes instead of calling them careless, after understanding her denominators and building her proofs, she realizes the 42 isn't a verdict.
It really is just a map. It's a diagnostic tool showing her the precise intersections where she took a left instead of a right.
And I think about when a project fails at work or a negotiation falls apart, do we just tell ourselves it was a careless mistake and move on to protect our pride? Or do we dig in and find the exact broken link in the chain of reasoning?
Right. Did we use the wrong denominator for our risks?
Exactly. Did we count the same problem twice because we thought order mattered? Did we skip the logical bridge and just scream our conclusion?
The moment you give the mistake a specific name, it stops being a source of shame. It transforms instantly into a tool for leverage.
That right there is the ultimate takeaway from this deep dive into Mathematics A. This textbook isn't a race to calculate numbers. It's a practice in seeing underlying structure.
Well said.
We organize our choices to make sure we count accurately. We organize our uncertainty to find true probability. We organize our reasons to find truth and prove it to others. And we organize our mistakes so we can actually learn from them without ego getting in the way.
It's a rigorous training ground for clarity.
It really is. As we wrap up today, we want to leave you with a final lingering thought to explore on your own. It builds on everything we've unpacked today, especially that brilliant insight from Mr. Mizuno. The denominator is the world you are considering.
It's such a powerful lens for human behavior.
Think about your daily life. When you face a severe disagreement with a colleague, a friend, or a partner, a conflict that just seems entirely impossible to resolve, where you feel like you are speaking two completely different languages.
We've all been there.
How often is that conflict happening? Simply because the two of you are unconsciously calculating your odds using completely different denominators.
Are you living in two different mathematical worlds?
You're operating in a world with 36 equally likely outcomes, assessing risk one way, and they are operating in a world with 11 unequal sums, assessing risk completely differently. Neither of you is necessarily doing the math wrong in your own head, but your worlds just do not match. Before you argue over the final fraction, maybe you need to step back and make sure you're both building from the same blueprint. Don't let the disagreement become a trap. Make it a map.